Hi, this is going to be an extremely short unit on something called double descent. So this is primarily an empirical observation about what happens as you go from a very small number of parameters in a deep model and to larger and larger numbers of parameters. And we don't understand the generalization properties of SGD run on deep models very well. In the last unit, I talked about implicit regularization, and I gave a Pack-Bayesian bound implicit regularization guarantee. But the problem with that guarantee is that the prior distribution is not something we can compute. So it's very difficult to do any kind of analysis based on that bound. You might be able to do some empirical experimentation, seeing what that bound might be telling us. But what I'm going to talk about today is fundamentally more empirical. And this is this phenomenon called double descent. And this has been popular for the last couple of years. There's this paper that appeared archived December 2018. And then one that was just iClear 2020. So what is double descent? So what I'm showing you here is test and train, but not over time. What we're looking at is after you let SGD converge, you take your learning rate to 0, you get your best possible model. Let's look at the training, the train and test error of that model as a function of the number of parameters. So what we're seeing here is the number of parameters, and we're starting at a very small number of parameters. Okay, so this is ResNet 18. So this is an 18-layer ResNet, and in any sane ResNet, you've got hundreds of dimensions at each layer, at each tensor, each little box at each layer, you've got hundreds of neurons at each position. But if we take the number of neurons at each position to be really small, like 5 or something, what happens? So it's a very limited model if it's only got 5 neurons at every position in the ResNet. So for a very limited model with clearly too few parameters, as we increase the number of parameters and the model becomes more expressive, its test error and its training error go down. And we have this theorem that says for very simple models, the test error and the training error will agree. So when we started in this regime, for very simple models, the test error and the training error agree. As we increase the number of parameters, we start to overfit, and the test error starts to get worse. The training error is still going down. So this is very classical. This is the classical bias variance trade-off that says there's a place where the test error starts to get worse. You're overfitting here. But now this weird thing happens. You let the number of parameters get larger, and your optimal model starts to perform better, not worse. And it ultimately is going to perform better than that point. So this is called the double descent as a function of the model complexity. So this is the width parameter of ResNet 18. And this is a different presentation of the same effect. We've got the converged in purple here. That's the converged model, which was what we just looked at. But here, the different colors are now going through time. This is still the width parameter, but we're going to, what if you just run 1 epoch, 2 epochs, 3 epochs? So what's happening is you get these different curves as a function of time. Now, you can always early stop. So as you're going through time, you're looking at your validation data, which is serving as a kind of test data, and you stop in time. You stop your epochs, you stop your training when that validation data is minimized. And so this red curve is the generalization loss, the validation loss at the early stopping point. And early stopping, if you early stop, you're always going to get better. Early stopping is something that you might as well always do. But what you see here is that the converged, if you just run always to convergence, you don't early stop, you just run to convergence, eventually, as the number of parameters get large enough, you might as well run to convergence. There is no early stopping point. These two lines become the same. And this is a phenomenon that probably what's going on here is you're making a transition from a finite parameter bound to some kind of infinite, like infinite dimensional bound, more like a kernel, which has always worked with infinite dimension. And then there's some implicit regularization that we don't really understand going on with SGD. So the intuition is there are these two regimes, the sort of classical story regime where you overfit, and this other regime where the number of parameters can be very large. And the modern trend is to just let the number of parameters be as large as your hardware can support. People are starting to train trillion parameter language models. So that's double descent. And now we're going to move on to new topics. I'll stop there. Thank you.